this last question, that is question number 8, consider the following subsets of the planes. Subset of the plane C1 is x comma y such that x greater than 0 and y is equal to 1 upon x. And C2 is x comma y, x less than 0 and y is equal to minus 1 plus 1 upon x. So you can see this is rectangular hyperbola, one of the branch. The first one C1, this will be like this. Okay, and in C2 this is another again rectangular hyperbola, but we have lowered the value by minus 1 or lowered the value by magnitude 1, and this is for x less than 0. So if I draw this line y is equal to minus 1, okay, so this is how my other C2 would be. This is C1, this is C2. Okay, now we are given 2 points P equal to x comma y, Q is equal to u comma v of the plane. Their distance is defined by under root of x minus u whole square plus y minus v whole square. That is just a normal definition, nothing special about it. Now we have to show that there exists a unique choice of P naught at C1 and Q naught at C2 such that distance of P naught with Q naught is less than or equal to distance of P with Q for all P belongs to C1 and Q belongs to C2. Now please listen carefully. Actually we need to find a point P naught here and maybe Q naught here so that the distance between these 2 points is least possible among all possible pairs, one of the point lying on C1 and other point lying on C2. That is what we need to prove. I think we can use the simple concept that least distance lies along common normal. In fact, among common normal we may get maximum distance also. In fact, these least or maximum distance which I am talking about, they are always local minimum or local maximum. So we have to verify also whether using this common normal thing we will be getting absolute least or not. To do that, let us do one thing. Let us take P naught as t comma 1 upon t and Q as s comma minus 1 plus 1 upon s. Okay, now because P naught Q naught will be along common normal, okay, so I will be writing the slope using 3 methods. Okay, so slope of normal at P naught, you can check, it will be just differentiate with respect to x, you will be getting minus 1 upon x square. And because slope of normal we are talking about, so minus 1 upon slope of tangent we will be getting this to be t square. Easy thing, it can be done directly. Similarly, slope of normal at Q naught, it will be, I think, s square. So we will be getting t square is equal to s square, and also this slope should be given by slope joining 2 points. So it will be 1 upon t minus 1 upon s plus 1 whole divided by t minus s. Okay, I can write the last term also as, I think, minus 1 upon t into s plus 1 upon t minus s. These two terms, if I take LCM, s minus t upon ts, t minus s will get cancelled, minus 1 upon ts plus 1 upon t minus s. And this is here t square is equal to s square also. So if I simplify it, or let me write it once again, t square is equal to s square is equal to minus 1 upon ts plus 1 upon t minus s. Okay, now this means t will be equal to minus s. Why I am saying so? T cannot be equal to s because t is positive and s is negative. So this t will be equal to minus s, and then if I combine these two things, so writing s is equal to minus t, I will be getting t square is equal to 1 upon t square plus 1 upon 2t. Okay, this gives us a biquadratic t power 4 minus 1 upon 2 into t minus 1 is equal to 0. Okay, so the root of this biquadratic will give me where common normals are possible. Okay, and then we will check whether these common normal will be giving least distance or not. Let us see. First of all, the root of this, if I check, this is a biquadratic. It will be having infinity values at both ends, minus infinity and plus infinity. The value at 0 is 1. If I call this as ft equal to t power 4 minus t by 2 plus minus 1, you can see f dash t comes out to be 4t cube minus 1 upon 2. Okay, and if calling this is equal to 0, I think will give us only one value, that is t is equal to uh, I think 1 upon 2 only. T is equal to 1 upon 2. Yeah, that is correct. And if we check the sign of this f dash t at 1 upon 2, it will be positive here, it will be negative here. Okay, so for this ft, this point will be point of minima. In fact, we can draw the graph of ft. I'm not talking about these graphs C1, C2. I'm talking about the graph of ft. The value at 0 is 1, minus 1. At 1 by 2, it's minimum. So it will be going down till 1 by 2. And then it will be going up because this was the point of minima. And because this is the biquadratic, it has to move up, so there will be one point where it will become equal to 0. My t is positive because I have taken this t on C1, so I need not to make this part of the graph, and this point is not relevant to us. So we can see this ft will become 0. So ft is equal to 0 only at one point. Only at one point. You can call this as t is equal to, let us say, t naught. Okay, and this t equal to t naught will be the point where p naught, q naught will be having a common normal. Okay, and here you can see this common normal will either give us local minimum distance or local maximum distance. By simple observation also, it can be said directly that if you go any further from this point to here or this point to here, distance is going to become more than what p naught q naught will give us. In fact, there is a possibility that we may have points lying on C2 and C1 such that the distance is infinity also. So there is no question this becoming a point of local maximum. It has to be point of local minimum. So this t naught given by this ft is equal to 0 will give us p naught, and then correspondingly we can find q naught also. And we need not to find p naught q naught. They are only saying that we have to prove that there exists unique choice of p naught and q naught, so that distance of p naught q naught is less than or equal to distance of p comma q for all p belongs to C1 and q belongs to C2. So I think this way we are done with this.